Okay, let's look at this one, which is trigonometric. I'm restricting the domain here for you because in general, trigonometric functions, of course, are periodic, and so to find all the critical points, there'd be an infinite number of them. So we're just considering values between negative pi halves and pi halves. So the domain is already done for us. Let's go ahead and do the first derivative test by taking the derivative. The derivative of tangent is secant squared. So I want to know, where is this either 0 or undefined? Secant is a reciprocal function, so it would be pretty natural for me to think of this as 1 over cosine squared. And now I've got my fractions, so I want to get a common denominator. So I'll multiply the first fraction by cosine squared. And so I can write my derivative as a single fraction. Now I want to know, where is this derivative? This is my derivative. Where is my derivative either 0 or undefined? Well, the derivative will be 0 wherever the numerator is equal to 0. And it'll be undefined wherever the denominator is equal to 0. So I want to solve these two equations. So here I'm really looking for, if I bring the 1 over and divide by 2, I'm solving cosine of x equals square root of 2 over 2, right? So it's really the square root of 1/2, or which can be rationalized as square root of 2 over 2. It's more naturally seen like this. This would help you in terms of unit circle, recognizing that this is going to be at, so pi over 4 would be the sort of first choice I think everyone would choose. But remember that we're restricting our domain really from negative pi halves to pi halves. So when I'm solving on my unit circle, I'm thinking about in the first quadrant and also in the fourth quadrant. Now, but instead of writing the fourth quadrant as 7 pi over 4, which is not in this domain, I want to pick the one that's coterminal to it that's in this domain. So that would be negative pi over 4. So my two solutions in this interval would be negative pi over 4 and positive pi over 4. Over here I'm solving, where is cosine of x equal to 0. So cosine of x is equal to 0 at negative pi halves and pi halves. But both of those are not in the domain because the round parentheses says we're not including them. What's really happening here is, of course, the domain is, tangent is not defined at negative pi halves or at positive pi halves. So there's vertical asymptotes there, which is, of course, why the derivative is undefined there. Anyway, so we have two critical points happening. We have at pi over 4 and negative pi over 4. Certainly there would be an infinite number of critical points if we were really looking on the entire domain, right? But we're restricting just between negative pi halves and pi halves. Okay, so I really don't want to like have arrows here. I really want to think of this whole thing as, I don't want to go to the left of negative pi halves. I really don't want to go to the right of positive pi halves. But I do want to look at what's happening in between these intervals with the negative pi over 4 and the pi over 4 here. So it really breaks it up into 3 intervals, my 1, 2, 3. But when I pick something to the left of negative pi over 4, I don't want to go so far away that I'm outside of the original domain. So I really need to pick something between negative pi halves and negative pi over 4. If you have a hard time with this because it's in terms of pi, go ahead and convert these to decimals and then pick a decimal in between here to actually evaluate your function. What you should get here for the first derivative is that it's negative on this interval, then it's positive, and then it goes back to negative again. So my function is decreasing, then increasing, then decreasing again. This is for f, of course. So if we go from decreasing to increasing, we get a local minimum at negative pi over 4. And then if I put negative pi over 4 back into my original function, I get negative pi over 2 plus 1. And then I'm going from increasing to decreasing, so I get a local maximum at pi over 4. And if I put pi over 4 back in, let's see, pi over 4 times 2 is pi halves, and then minus 1. So why do I feel like something's wrong with my answer key here? Where we would get pi halves, and tangent of pi over 4 is 1. I think that's right. In fact, let me just double check it. I'm going to pause this for a second. Okay, so I think I was right here. Okay, so now where were we? We have our local minimum, we have our local maximum, and so now we have to do the whole thing again for a second derivative. Now let's see if I have a little more room down here. I guess I'm going to, maybe I'll change color so it makes it easier to find. Okay, so now let's do the second derivative. So second derivative, so derivative of the 2 is going to be 0. And then now I'm going to have to do a either quotient rule or I think chain rule on this. So I'm going to think of this as a negative 2 secant of x to the first power times the derivative of secant, which is secant times tangent. If you didn't remember that rule, which is totally fine, you could just think of it as 1 over cosine squared and do it that way. So anyway, here we're left with negative 2 secant squared times tangent. If I want to try to write this as a ratio, it makes sense to write these as in terms of sines and cosines. Right? And then it naturally just writes itself as a ratio. So negative 2 sine of x over cosine cubed of x. So I want to know, where is this thing either 0 or undefined? It's going to be 0 anywhere the numerator is 0, which is the same place sine is 0. Sine will be 0 at 0, and then nowhere else in the given domain. And where is cosine cubed going to be 0? Well, that'll be wherever cosine is 0, and that again is just going to be values outside of our domain, negative pi halves and pi halves. So we don't get any new information there. We're just looking at x equals 0. So I'm kind of squishing here for our second derivative, our concavity test here. I'm going to fit right here. We're looking at values to the left of 0, but remember, don't go too far. We want to stay within our original domain. So between negative pi halves and 0, it turns out the second derivative is positive, and then after that it's negative. So we've got concave up switching to concave down, which gives us an inflection point. Sorry, I'm all over the place here. An inflection point at 0, comma. If I plug 0 back into the original, I get 0. Okay, so let's try to sketch this thing, all of the information that we've got. Let me change colors again, just to try to make it not all on top of each other. Okay, so we have negative pi halves, and at pi halves is our vertical asymptotes, so we're really sticking just between these two values at pi halves and negative pi halves. We've got an inflection point at 0, 0. We've got a local maximum at pi over 4, comma, pi halves minus 1, and then we got a local minimum at pi over 4, comma, 1 minus pi halves. Okay, we are decreasing all the way up to here, and we're decreasing concave up. So what does it look like to be decreasing concave up? And then we are staying concave up until I get to 0, but now I start increasing. So concave up, increasing. Then I switch to concave down, right, because here's my inflection point, but I stay increasing. So concave down, increasing. And finally, decreasing again, still concave down. So I'm going to just head down towards my asymptote. And my asymptote got a little curvy there. But so that's the idea. It sort of comes down, goes back up, and then comes back down again. And pretend my asymptote is straight there. Sorry, not my best graph. All of these you should be double checking on your graphing calculator just to make sure that you're getting the same thing.